Okay, now let's look at, in the previous videos we were looking at gases, and we saw that gases were compressible. That means that if you remember, if you take some column of gas, we saw that lower down they had a higher density, mass density, than as you went up from the earth, or from sea level rather, became less and less dense, right? So gases were compressible. However, liquids are nearly incompressible. What does this mean? It means that the density in a liquid is basically constant everywhere. Okay, it's the same density, it's uniform. So this allows us to derive a simple expression for how the pressure changes in a liquid. Okay, so let's consider this container with a liquid in it. Okay, and we want to consider a cylinder, basically an imaginary cylindrical volume of liquid. So here is our cylinder. Okay, and we want to kind of see what's happening to this guy. Okay, so this is called point 2, and that's called point 1, and that is depth y2, and that is depth y1. Now let's draw a free body diagram of this cylindrical volume of water. Okay, that is the body, that's the free body. Okay, now what are the forces acting on this body of water? Well, down here at point 1, we've got this body of water over here, right? That body of water acting up, and this is called F1c, acting up. So it's the force of this body of water at the bottom, applying a force to keep this body of water up. Okay, F contact 1c. All right. Then we've got the force of this body of water over here pressing down. This one over here pressing down at 2. That's F2c. Okay. And as you can see, F1c is much larger than F2c. And then we've also got the gravitational force acting on this body of water. So force of gravity, Earth, on the cylindrical volume, C. Okay, so you've got these three forces. Okay, I hope that makes sense. Now the important thing to see is that we are dealing with, in this section, we're dealing with a stationary body of liquid. A volume of liquid that is at rest. Okay, it's not moving. Okay, please take note of that. Okay, so the acceleration is 0, and so we've got these three forces, and if the acceleration is 0, then these forces balance out. This force, the magnitude of this force, equals the sum of the magnitudes of these two forces. Okay, so we've got F1c plus F2c plus the force of gravity, right? These three forces, if you add them up together, you should get 0. What are they though? Well, if we convert them into a kind of a pressure description or representation, remember that force is pressure times area, or pressure is force over area. That's the basic idea. So this force 1c acting up is equal to the pressure at 1, okay, the pressure at point 1 there, multiplied by that surface area there, that surface area. So P1, pressure at 1 times A, okay, and we take up as positive, then minus P2, the pressure at point 2, multiplied by the same area. It's the same area, okay, and that's acting down, so it's minus, okay, so it's minus that force times that area. And then we've got minus mg. What is the force acting on this mass? It is the mass of that fluid, the mass of this cylindrical volume times gravity. All right, happy, great. Okay, So if we now look at this mass over here, let's write it in a different form. We know that mass is density times volume. So it's the volume of this cylindrical volume, it's the volume of this cylinder, multiplied by its density. That gives us the mass. So let's replace this mass with rho V, and then V becomes, what is the volume? It is the cross-sectional area times this height, which is y2 minus y1. y2 minus y1. Okay, that height there. Okay, I hope that's clear. So all we've done is we've taken that mass and replaced it by rho V, and we've replaced V, the volume, by area times height of that column of liquid. Okay, so if we rewrite, we get pressure 1 times area minus pressure 2 times area minus density times area times the height times gravity, and this is equal to 0. And then if we rewrite this guy, we get this expression for a stationary liquid. Stationary, zero acceleration. Okay? Static. Another way is static. So what is this telling us? At point 1, we have P1, P1 plus rho g y1, okay, is equal to P2 plus rho g y2. And if you chose another point, say 3, if this was deeper, you could have P3 plus rho g y3. And so there's two things that we need to see from this. The one is that this quantity, pressure, plus density times gravity times the depth at which you're measuring that pressure, is the same everywhere in the entire liquid. And then from this, a very, very, very important thing that we need to see is that if you consider any horizontal plane through the liquid, okay, so any point along this horizontal plane, the pressure there is the same as the pressure there, is the same as the pressure there, is the same as the pressure there. Okay? The pressure in a stationary liquid is the same at all points in any given horizontal plane through the liquid. Okay, guys? Important point. Please absorb that. Now, if you again rewrite this into a more intuitive way of understanding it, we get this. You get this. For a stationary liquid, and point 1 is below point 2. Take note, point 1 is below point 2. So this, what we've just derived, guys, is if I want to know what is the pressure here, but I know what the pressure is over there at point 2, then what this tells me is that the pressure at 1 is equal to, let's rewrite this, if there's point 2 and here's point 1, the pressure at point 1 is equal to the pressure at point 2 plus the density of the liquid times gravity times this distance d. Okay, do you see that? So the pressure at point 1 increases, is higher than the pressure at point 2 by this quantity, rho gd. So you can see it's a linear relationship. The density is constant, gravity is constant, and d changes, it increases, right? So P1 is simply going to be whatever this pressure was plus this linear function of the depth. Okay? Now, how we can further apply this is by assuming that point 2 is on the surface. Okay? So if we know what the atmospheric pressure is, then all our pressure at any depth in the liquid, in this fluid, in this liquid, okay, not fluid, okay, because fluid includes a gas, so I'm talking about a liquid. an incompressible liquid. Then if we know what the pressure is, the atmospheric pressure is, all we need to do is compute rho GD, and then we know what the pressure is at this point. Okay? So this expression shows that the pressure P in a stationary liquid increases with depth, or put differently, P increases linearly with the height in the liquid. So it decreases as you increase the height, and it increases linearly. Notice, guys, linearly. Okay, so it's going to have some kind of function like this, right? Something like that. Okay, excuse my drawing, but there's a linear function. This is a straight line. It's not like gas where it did this, right? That is a non-linear function. There was a linear function. Okay, last 10 seconds. The term that contains G, this guy, is the gravitational contribution to pressure, and is sometimes referred to as hydrostatic pressure. Now recall, we spoke about what contributes to pressure in a fluid. There was the gravitational effect. There was also the motion effect, not motional, when a fluid is moving, and there's also the surface effect, which is in a later section. Okay, so we've covered this first aspect, the gravitational effect.